Hello everyone, you're watching The Maths Geek. In today's video, we will be discussing a proof of the factorial integral formula. This formula is a representation of the factorial function as an integral. The factorial function is the function which is the product of numbers from 1 to n, denoted by n factorial, n with an exclamation mark. So today we are going to prove that the integral from 0 to infinity of x to the n times e to the minus x dx is equal to n factorial. Now there are two methods of proving this of which I know. The first one is using something called the Leibniz rule of differentiation under the integral sign, and the second one is using basic induction. So let's go on into both of the methods. The first one is using the Leibniz rule. So first, let me just write down the result. So we have to prove this. When we integrate x to the n times e to the minus x from 0 to infinity, we get n factorial. So now we are going to look at a simpler integral which will help us reach this integral eventually. So what we are going to look at is this. The integral from 0 to infinity of e to the minus ax dx. What is this? Where a is a positive real number, any positive real number. So now this thing is a very basic standard integral, and the antiderivative of e to the minus ax is just going to be minus 1 over a times e to the minus ax. You can just check that by differentiating this to obtain that, and we evaluate this from 0 to infinity. Okay, so now first I'll just get my minus 1 over a out, and now if I plug in infinity, what I'm basically doing is taking the limit. So I'm taking the limit as x goes to infinity of e to the minus ax. Now ax is also going to go to infinity, because a positive infinity, because a is a positive real number, and therefore minus ax will go to negative infinity, and that means e to the minus ax will naturally go towards 0. So at infinity, this is 0, and at 0, e to the minus a into 0. Anything above anything times 0 is 0, any positive real number, so we get 0, in fact, any of those. So e to the 0, which is just 1, and we do minus 1 here. So the final result is just 1 over a. Now, you all might be confused as to why I am doing this, but this will be the stepping stone which will help us prove our final result. So now, using this fact, we are going to write this. I'm going to write this down here, and this is 1 over a. And now I will apply. Okay, sorry about that, and we move on. So now I'm going to apply the Leibniz rule of differentiation under the integral sign. And now, according to this rule, if an integrand is, you know, it accords with certain rules, then we can differentiate the integral, and we can set that equal to the derivative of the right hand side. So now let me write this like this, and now I'm going to differentiate with respect to a on both sides. And now if I just differentiate 1 over a, that's basically just a to the minus 1. So by the power rule, the minus 1 comes down and this becomes minus 2. So it's just minus 1 over a square. Okay. So now I just get that this is equal to minus 1 over a square. And now, according to the rule, we can actually bring this derivative differentiation inside and make it a partial derivative. So this becomes this a partial derivative of e to the minus ax dx. Now, if you all know a bit about partial derivatives, what we do is we differentiate, but we take the thing which is not related to this as constant and we bring it out. So we get the minus x out, which is not related to a, and we treat that as a constant. And now we write this finally as this thing minus x, which comes out, times e to the minus ax dx is equal to minus 1 over a square. So I'll just box this thing and we'll note this down up. Okay, so previously what we had gotten was this minus x times e to the minus x dx. This is negative 1 over a square. Now I want to differentiate this again and see if there's a pattern if I go on differentiating n times. So again, if I differentiate both sides, sorry, so if I differentiate both sides, I get what? Again, I take the partial derivative, so the minus x comes over, and this time this becomes minus x whole square. You will see why I'm not writing this as x squared. Just a second. E to the minus ax dx. And now if I differentiate minus 1 over a square, again, it's just the same thing. A to the minus 2 and the minus will just stay out because of the product rule. So this minus 2 comes over and becomes plus 2 because minus into minus is plus, and this becomes 1 over a cube. So it's 2 over a cube in all. R R H S. Okay, sorry about that, and we continue. So now let us differentiate again, and let's see if you all can probably find a pattern. So again, if we just differentiate this on both sides, again this becomes minus x whole cube. The minus x just comes over due to the rule, and now this will become minus 6 because it's 2 times a to the minus 3, and 2 times minus 3 is minus 6, and the denominator is just a to the 4. Okay, so now I hope a pattern is emerging to some of you. What you can notice as when the exponent of negative x was 1 here, what we got was minus 1 to the first power. So when this was 1, then we got minus 1 to the first power times 1 factorial over a to the 1 plus 1. And now again, if we there is 2 here now, minus 1 to 2 is minus 1 to any even power is just 1. That's what happened, that's 1. And you multiply that by 2 factorial, and then you divide by a power 2 plus 1. The same follows here, that for 3 you just get minus 1 to the third power. You can notice that at all the odd powers, there's always going to be a negative sign on the RHS, and at the even ones, it's just going to vanish. So minus 1 to the third power times 3 factorial over a to the 3 plus 1, which is a to the 4. So now using this, and you can just do this recursively and show that if we go n times into this thing, keep continue differentiating, what we are basically going to end up with is just as I wrote it out. So now we can say that if I do minus x to the n times dx, that's going to equal minus 1 to the n times n factorial over a to the n plus 1. Now I just don't need the minus 1s to the n on both sides, so I can just divide by them, and since it's a constant, so we just get this. So x to the n times e to the minus ax dx is equal to n factorial over. Now remember what I wrote at the starting, a could be any real number for our first integral of, for this integral of ours here. I wrote that a could be any positive real number, and now we pick a very appropriate and convenient value of a, which is just going to be 1, which will yield us our result. So just putting a is equal to 1 over here, just notice that e to the minus ax just becomes e to the minus x, and therefore we can write that the integral from 0 to infinity of x to the n times e to the minus x dx is just n factorial, and we are done with the first way. So I hope you all understood this. What we basically did was we took a simpler integral, used the Leibniz rule, differentiated it, saw a pattern emerge, and then generalized it and put an appropriate value of a. Alright, so that was method number